to me. Okay, so let me finish up. I'm going to finish up with everything I want to say about the Hitchin-Simpson theorem. And then since Jacques raised the issue about unstable bundles, I want to say something about those today as well. So let me begin with the definition. So let's fix a Higgs bundle. E phi on a compact Kaehler manifold omega. And here I'm going to assume that this is E is a holomorphic bundle. So this is a holomorphic bundle with a Hermitian metric. So it's a Hermitian holomorphic bundle. So the underlying C infinity bundle, sometimes I'll write E, and this has a fixed metric. So there's an initial Chern connection. This is the Chern connection. Associated to this bundle. And here, let me call this phi 0. Okay? So I want to define a heat equation. And so here's the flow. So this is this is the Hermitian flow. So what is it? It's so here I'm going to define a family of connections, unitary connections that depend on time. So t is my next variable, and so this is the Yang-Mills, the usual Yang-Mills flow, which would be this term. And now, of course, we're going to add in the part coming from the Higgs field. So here again, A is now a family of connections, and phi is a family of 1-0 forms with values in the endomorphism bundle. And there's also an equation for how phi evolves. And this is, I might be wrong on this sign, but, and then this is I, the contraction of Okay, so this is the Hermitian Yang-Mills flow, and I can impose an initial condition that A of 0 is my initial Higgs bundle, and phi of 0 is my initial Higgs field. Okay, and so this is the evolution of bundles with Higgs fields, and the statement is that actually these are Higgs bundles. And in fact, they're all isomorphic to the original one. So the theorem, let me state this in a theorem, which is due to Donaldson, is that the flow exists for all time the flow is this equation over here. And in fact, and is and AT PT is in the complex gauge orbit of the initial Higgs bundle. In particular, these are Higgs bundles themselves. This is a Higgs bundle. And in fact, it's isomorphic to this one. So there's an isomorphism GT, which takes me from the original Higgs bundle E phi 0 to say E sub t phi of t. Okay, but the flow exists for all time, which is already rather remarkable in the sense that if you look at just the Yang-Mills flow, where you turn off the Higgs field, and if you look at the Yang-Mills flow on a Riemannian manifold, this makes sense on a Riemannian manifold, no complex structure or anything like that. It turns out the Yang-Mills flow in dimension 5 and higher is known not to exist for all time in all cases. There are exceptions where it does not exist for all time. So, the existence for all time is already quite remarkable. The problem here being that, maybe I've said this before, is that there's this gauge invariance, and in fact here I should say up to gauge, right? I'm always assuming things up to gauge transformations, up to unitary gauge transformations, and because of this gauge invariance, you can have blow up of the solutions in general, and but on the Kaehler manifold with holomorphic initial conditions, that doesn't happen. Okay, so so this is very nice because this gives us an example of by massaging these equations, what we can find is so then there exists a subsequence yeah, so ET is the holomorphic bundle E d bar AT. So this is an integrable holomorphic structure, and that's what I mean by ET. Not yet, not yet. So the flow always exists for all time, for anything. So then we get a subsequence, AJ, BJ. There exists a subsequence such that AJ, PJ minimizes the energy. I guess I haven't really told you what the energy is, but minimizes the energy in the complex gauge orbit of the initial condition, A naught, B naught. This tensor, this is the Hermitian-Einstein tensor, phi star, is uniformly bounded, so put a T everywhere, is uniformly bounded. Oh, sorry, I should put a J since I'm taking a subsequence. Okay, this is like the uniform Lipschitz of the maps in the Corlett theorem. And then finally, this is the other condition that I mentioned, is that d AJ star of FA star of J phi J phi star J goes to 0 in L2, and also the bracket of phi with the Hermitian-Einstein tensor also goes to 0. Okay, so these are the favorable things that you would want to conclude that if there's a limit, it should be a Higgs bundle, first of all. Right? So you'd like something to be converging to a minimizer. A minimizer should be a critical point of this energy functional, which are the solutions to the Hermitian, the Higgs Hermitian-Yang-Mills equations. And so this is exactly what you would like to get. And so now you see what's happening here is that we have a bound on the Hermitian-Einstein tensor, but not really the Hermitian-Einstein tensor of the connection, but of the connection plus this bracket of Higgs fields. And so in the Uhlenbeck compactness theorem, there's something missing. So we have to improve on this. Actually, let me just first of all state the theorem, because I'm going to get ahead of myself otherwise. So here's the theorem, is that if A0, B0 is a stable Higgs bundle, or polystable actually is fine, then the flow converges smoothly actually to a solution of the to a solution, let's say A infinity, phi infinity of the equations of the Hermitian, the Higgs Hermitian-Yang-Mills equations, the ones that we want, and A infinity, P infinity is isomorphic through the initial bundle. So this solves our problem, in other words. So that's not the way I phrase the problem. I phrase the problems in terms of looking for a metric. But what happens here is that through this isomorphism, so there's some isomorphism, what I can do is I can pull back my initial metric. Sorry, I can pull back the metric under this isomorphism, and that gives me a metric here for which I get a solution. So there's equivalence between complex gauge transformations and changing the metric. Okay, so this is a point that I'm sort of sweeping under the rug here, but finding a solution to the Hermitian-Einstein equations in the limit that's isomorphic to the original bundle is the same thing as finding a metric on the initial bundle that solves the equations. So that's the theorem. So it's a little bit stronger statement than just saying that there exists a solution to the original equations. It's also saying something about the flow. So of course this is a theorem of Donaldson for stable bundles when you turn off the Higgs field, and Simpson in general. And so let me just say a historical comment, is that in the case of stable bundles, the proof of the existence of Hermitian-Einstein metrics is due to Donaldson, on the one hand, for algebraic manifolds, and Uhlenbeck-Yau in general for Kaehler manifolds. So Donaldson used the heat flow, but then to prove this last little step, that this limit, that the convergence of the flow at t smoothly as t goes to infinity, to prove this convergence, he needed to make an assumption of projectivity of the manifold. Uhlenbeck and Yau use a different argument. But on the other hand, they don't use the flow, they use the continuity method, which is kind of very, very similar in spirit to the flow, but strictly speaking, it's different. And what Simpson did was he kind of took the best of both methods and combined them together in the setting of Higgs bundles. So he used the heat flow in the context of Kaehler manifolds and used the last little argument of Uhlenbeck and Yau, which works in complete generality, to prove that in fact this flow converges. So in some sense, Simpson is so I should put Uhlenbeck-Yau's name here as well. Okay, so that's a little historical note. All right, and so as I say, so I'm not going to say too much about all the details here, but let me just say that again, I'm going to rewrite Uhlenbeck's compactness theorem here. So if I have a sequence of connections and with bounded, uniformly bounded Hermitian-Einstein tensor, then there exists a convergence subsequence, and this is weak convergence off a set which I will call Z, let me give this a name, Z analytic of codimension 4. And moreover, if I also assume that dAj star of Faj is going to 0 in L2, then that implies that this limit, A infinity, is a Hermitian-Yang-Mills connection. And in fact, it extends off of codimension 6. So in dimension 4, this will extend as a smooth Hermitian-Yang-Mills connection. Higher dimensions, it might not extend everywhere. There might still be residual singularities, but it extends off the pure codimension 4 piece. So I'll come back to this later if I have time. Anyway, so this is Uhlenbeck compactness, and so the rough idea of this proof is to say, okay, you've got this bound on the Hermitian-Einstein tensor. Let's consider first the case where we don't have a Higgs field. you have a bound in the Hermitian-Einstein tensor, you use Uhlenbeck compactness to get a limit, at least. So we get a limiting bundle, and then what? So then the idea is that we take these gauge transformations, okay? Now these gauge transformations might not, these are all isomorphisms, okay? But they might not converge, okay? So what we do is we rescale these, so the idea of the proof is to rescale the GJ to get a homomorphism, a non-zero homomorphism. From our original bundle, phi 0, E 0, to this limiting guy. So I don't know what to call this, maybe H or something. Okay? So this guy, so this requires an argument to know that we can actually rescale these G's so that they converge to something non-zero. Now the point is that it might not be an isomorphism anymore, but if it's not an isomorphism, we can look at the kernel and we can hope that that kernel would destabilize this bundle, and that would be a contradiction. Okay? So you can sort of see it's very, very similar to what the kind of argument we used in Simpson's proof. Okay? So there are tons of details here that I'm leaving out, but that's just the very, very rough idea of the proof. Okay? And that's basically how it goes for the Hermitian-Einstein case. And it's also basically how it goes in the Higgs bundle case, except there's one thing missing, namely, we don't have a bound on the Hermitian-Einstein tensor. We have a bound on the Hermitian-Einstein tensor plus this gadget here. So then a miracle happens, a miracle of linear algebra. So here's a linear algebra lemma. If you're bored with the talk, you can spend the rest of the 60 minutes trying to prove this. It took me a long time, actually, to come up with a proof. Linear algebra lemma. So this is actually stated without proof in Simpson, basically. Or he sort of gives a proof. I shouldn't say without proof. But linear algebra lemma. So fix a constant b. Then there exists constants C1 and C2, such that if P is a matrix with with the spectrum of P contained in minus BB, so the eigenvalues of P are bounded by B. Then, if I look at the norm of P star squared, that's bigger than some constant times the norm of P to the fourth minus some other constant times, say, 1 plus P squared. No, exactly. Okay, so, well, we can philosophize about the meaning of this inequality, but I think it's kind of a beautiful linear algebra fact. And it's exactly what we need in this case. So this lemma, combined with the Weizenbach formula, an easy Weizenbach formula, nothing sophisticated here, gives the following. So let's say a proposition here is that if the eigenvalues of our Higgs field phi so here I just have a Higgs bundle. And if the eigenvalues of phi are bounded by B, then there exist constants, I may as well call them the same thing, such that the sup norm of phi squared is less than one constant plus another constant times the sup norm of this funny Hermitian-Einstein tensor. All right, so I'm not going to go through the details of this. It's some calculation. I can give you a reference if you're interested, but this is exactly what we need. So this, again, follows basically from this lemma. Unfortunately, I'm not going to. Here, yes. Exactly, that's why I have a minus sign here. Exactly, that's the whole point. So what you'd like to say is that pp star squared should roughly be p to the fourth. So in this formula, we want to find a lower bound on this by p to the fourth. But of course, that's nonsense because this commutator could be 0. And so you have to allow for that possibility. And the point is that the only thing you have to do to allow for that is add a quadratic term in p. That's enough. No assumptions. Oh, sorry. Absolute value. I was trying to be cute here, but the eigenvalues with eigenvalues of p bounded in absolute value by b. Yeah, thanks. That's yeah. Oh, that was misleading. Okay, so this basically gives us what we want now, because now we know that this bound on the Hermitian-Einstein tensor actually gives us a uniform bound on the phi, and so we can forget about this part. In fact, we get a nice uniform bound on the Hermitian-Einstein tensor itself. Okay? So this argument then goes through. Okay, so I think that's, of course I'm leaving out many details, but I think that's about as much as I could possibly hope to say about this. But the reason I go through some of the details is because I want to point out one thing that we've sort of seen a couple times already in other lectures this week, and that's the properness of the Hitchin map. So let me erase this here. Yes. One has to be careful. So one has to be careful. That's right. So here by an isomorphism, I really mean, again, off this singular set Z. That's well, actually, this extends a little bit further. Okay, so I really mean an isomorphism there. But of course, once I know that's isomorphic to the original one, then I know it extends. So, but one does have to be a little bit careful about that Z, and especially when one does the rescaling here of this guy. Yeah, one has to remember that you don't have good estimates around Z. Okay, so as a corollary, not corollary of the proof, rather, of this particular proof, we get that the Hitchin map is proper. Okay, so there, the full power of Uhlenbeck's theorem is not really, well, you still need it in some sense, but you can show that this set Z is actually empty in that case. But so what do I mean by the Hitchin map? So i.e., if, let me state a more precise result here. So if EJ EJ is a sequence so in M Higgs is a sequence in M Higgs such that the eigenvalues of phi are uniformly bounded, okay, that makes sense because that's independent of the isomorphism, of the representative of the isomorphism class. So if the eigenvalues are uniformly bounded, then that implies that there exists a convergent subsequence. Okay, so it's again this same Uhlenbeck compactness argument. In that case, this is actually 0. So in some sense, the inequality is even sharper, but nevertheless, you still need to use this kind of Uhlenbeck compactness type argument. Okay. So in particular, if I look at the action of C star, so here lambda is in C star, and I take lambda of phi. So I start with a stable Higgs bundle. Then lambda of phi, of course, if you go back to the definition, it's still stable because the only role of phi was to determine invariant subbundles, and that doesn't care about the scale of phi. So this is clearly stable if the original bundle was stable. And what this theorem says is that when I take the limit as this goes to 0, well, it's a little bit stronger than actually that the limit exists, but one can show that the limit actually exists. This actually exists. And now that's interesting. That's very interesting because, of course, the limit is not necessarily just the stable bundle with a trivial Higgs field, right? Because that doesn't necessarily have to be stable. So note that E is not necessarily stable. Okay? So that means that we're converging to some other Higgs bundle with a non-trivial Higgs field, but somehow up to this isomorphism, there must be some isomorphism here that undoes this lambda action on that limiting. So the limit, of course, exists and is a fixed point of C star. So there's an isomorphism, in other words, of that limit that undoes the action of lambda. So that means that this bundle has to be reducible, and then one can start to understand what those guys look like. And so those are the complex variations. Sorry? The limit Higgs field, sorry? The eigenvalues are 0. It's in the nilpotent cone, exactly, yeah. Yeah. So these fixed points of the C star action are what Simpson calls complex variation structure. And the fact that you can take any semi-simple representation of a Kaehler, if you have a semi-simple representation of a Kaehler group, what this says is you can always deform it to one of these guys, and that's the origin of these restrictions that I mentioned the other day that Simpson finds on Kaehler groups. As a limit, well, I mean, of course, if it's a fixed point, then it's a trivial limit. I'm a little bit confused. So I might have a rigid representation, for example, in which case it's automatically a fixed point. So there might not be anything else out there, right, in the component. There might be just this one little guy sitting there in that component. So we're not saying anything about it. That's a good question. I don't know. My first answer is no. This is just a compactness theorem here. Although that Mitsuri, so I should mention that Mitsuri has as a different proof, kind of an algebraic proof in the case of curves. And I'm not so familiar with that, so maybe, yeah. Yeah. Okay. So anyway, so this is what I wanted to point out about the C star action. Okay. So how am I doing on time? Very good. Any questions on that? So that's basically all I'm going to say about this. All right. So since I introduced the Yang-Mills flow, let me just spend, I guess, the rest of the time talking about what happens in the unstable case. So this is maybe not so relevant to the moduli space of Higgs bundles, but maybe it's of some interest anyway. So, okay. So the main question is, what happens to the Yang-Mills flow or the Yang-Mills Higgs flow if the original bundle Higgs bundle is unstable? Okay. So I want to give a complete answer to this question. So first of all, I have to introduce some. So first of all, let me just talk about Yang-Mills, just to simplify things a little bit. So let's, for temporarily turn off the Higgs field. Okay, it'll just, everything I say is going to go through in that case as well. But I just want to talk about stable, unstable bundles for a moment. So if E is an arbitrary bundle over a compact manifold, arbitrary holomorphic bundle, then, as I'm sure you know, it admits there exists a filtration. Let's say E, EL, L minus 1, etc. By saturated subsheaves. Such that these successive quotients, let me call them Qi, are semi-stable. With slopes, let's say mu I, and mu 1 is bigger than or equal to mu 2, etc. So this is the Harder-Simon filtration. And so I'm going to let GER of E be the associated graded. So just this direct sum of all of these pieces. Okay. Now, there's a further filtration where so there's a further filtration of each of these guys such that the successive quotients are stable. So that's actually what I want to work with. So let me just sweep that under the rug and assume that all of these quotients are stable. Okay, it's really harmless. I just have to do another filtration. But let me just assume that these are actually stable, okay? By assumption. Oh, sorry. No. The limit is a stable, because it's a limit of now of solutions to the equation. So we know that the limit, so I guess I wasn't very precise, but all of these guys, the way I proved this theorem is actually by solving the equations first and then taking a limit. And so as part of the Uhlenbeck package, the limit is also a solution to those equations. And we know that if we have a solution to the equations, it's polystable automatically. Yes, but it can still be stable as a Higgs bundle. Yeah. So in fact, you pointed out an example of that yesterday. So the key, oh yeah, that's a good point. I was going to mention that, sorry. The key example, a key example is what did I want to say? I wanted to say the opers. Sorry, I lost my train of thought now. Yeah, so that's right. So the key example are these is the non-trivial extension. So, sorry, the key example of a Higgs bundle that is not stable is an oper. In fact, the opers are the maximally unstable guys that emit holomorphic connections. So in fact, there are plenty of examples, and those. Okay. Right. So again, let's look at the Yang-Mills flow. So we have the Yang-Mills flow. Let me just say one thing first. So again, modulo this issue. So here I'm going to just for the after to another filtration, I can take another associated graded for each one of these guys. So here, this direct sum, the way I'm writing it, I'm assuming that these guys are stable. Okay. So in particular, they admit Hermitian Yang-Mills connection. Well, actually, they do on a Riemann surface, but not in higher dimensions. This is the point I want to make. So note, the QI are torsion-free by definition. That's what I mean by saturated sheath, is something that has a quotient that's torsion-free. And so let me remind you that the codimension of a singular set of a torsion-free sheath on a complex manifold is at least 2, and the codimension of the singular set of a reflexive sheath is in codimension 3. Okay? So on a complex surface, it's possible that these guys are not locally free. It's possible they don't come from vector bundles. Okay? But on a complex surface, I can take the double dual of this guy, which is the reflexivization of these sheaves, and in dimension 2, they will be guaranteed to be locally free. So let's assume for the moment that if dimension of X is 2, then less than 2, then Gur double dual is locally free, i.e. comes from a vector bundle. And there is a Yang-Mills connection on Gur double dual by taking the direct sum of the Hermitian Yang-Mills connections on each of the double dual pieces. Okay? So what do I mean by that? I mean a connection, i.e. A infinity, well, I shouldn't call it A infinity, A tilde, such that the, when I look at this Hermitian-Einstein tensor for A tilde, so this is a connection on Gur double dual, then it's not a multiple of the identity, but rather it's a diagonal matrix with the slopes of these guys exactly on the diagonal. Okay? So that's the form of the connection on GER double D. Okay, and so now there's kind of an obvious conjecture, right, about what happens to the Yang-Mills flow if I start in that initial condition. And so that's actually a theorem. State that theorem. Let me make one more definition here. So I'll call Z algebraic to be this, the support of the sheaf GER E double dual by GER E. Okay? So it's the support of, it's the place where GER E fails to be locally free. Okay, so let me just call that the algebraic singular set. Okay? So in the complex surface case, this is a collection of points. In general, it has codimension, complex codimension at least 2. So one last little piece of definition is that over here, so in the case of surfaces, the Z analytic that I've written over here is a collection of points. A finite collection of points. It's got finite Hausdorff codimension 4. So on a complex surface, this is just a finite collection of points. And in fact, there is a there's a multiplicity. So this is all Uhlenbeck stuff, right? It's a strengthening of this theorem over here, but this is all due to Uhlenbeck. There's a multiplicity associated to the points in here. And so multiplicity, let's say MP analytic, or P in Z analytic. And it's cooked up in such a way that if I look at the limit as J goes to infinity of this, of the measure, the energy density of the Yang-Mills equation, if you like. So I think of this as a measure, and so you would guess that if you have good convergence, it would be just the limiting thing, but of course we only have convergence away from the singular set Z, and so maybe this holds away from Z. In fact, it does hold away from Z, but there is a correction, and that correction is exactly given by the multiplicity times direct measures. Okay, so this is built into Uhlenbeck's stuff. Okay, similarly over here, there's also a multiplicity. Yeah, so for right now I'm talking about dimension 4. I'll get there. I will get to that, and I think I will get to that. Yeah, absolutely. So there's also a multiplicity here. Maybe I won't go into details here because, okay, but you can see this is manifestly so this is a torsion sheaf now, supported, it's a skyscraper sheaf at points, and over each of those points I've got a vector space, and that vector space has some dimension, and that's the algebraic multiplicity. Okay, so now I can state the theorem then. And this is due to Pascalopoulos and myself, is that if I start with A0, B0 over a compact Kaehler manifold, compact Kaehler surface, where A naught is integrable. So this is coming from a holomorphic bundle, and d bar A naught of phi is 0. So this is a, why am I doing the Higgs bundle case? I said I was going to turn off the Higgs field. So let me just do that. So suppose that, sorry about that. So I've got E with a d bar operator A0. Okay. Let me just ignore the Higgs field for the moment. So this is an integrable connection. So I've got a original holomorphic bundle. Then the statement is that the Yang-Mills flow converges smoothly this converges smoothly part is actually not us. This is Hong and Tian. But in any case, so we just said convergence in the Uhlenbeck sense, but actually they showed that it's smooth for the actual flow. So the Yang-Mills flow converges smoothly on x minus z algebraic to the Yang-Mills connection on Ger E double dual. So implicit in this is that the analytic singular set is actually equal to the algebraic singular set with multiplicity. So I should have pointed this out earlier. In Uhlenbeck's theorem, that Z, that analytic singular set, you don't know what it is in general. It can depend on the choice of subsequence that you choose for the connections. So there's no reason to expect in general that set has any sort of meaning in general. But in this case, it turns out that it's exactly the algebraic singular set. So you can really, really predict where you have smooth convergence of. So I defined two multiplicities. I've defined a multiplicity for the points in the analytic singular set, and I've defined a multiplicity for the algebraic singular set, and those two numbers are the same for each point. It's kind of like the higher dimensional version of that. Exactly. That's right. So Daskalopoulos, in the case of Riemann surfaces, proved this convergence. But there you don't have to worry about any singular set, and you don't have to worry about this double dual. That's right. So Daskalopoulos and Rode had done the case of Riemann surfaces. Okay. That's where I'm going to do next. So no. Right. So this guy is this. Did I get it backwards? Yeah. So you see, this Ger E is just a torsion-free sheaf. So it has singularities in points. Right. So this guy is locally free, and where does it differ from this guy? It differs from it in points. No. This is complex codimension. Complex codimension 2. Complex codimension 2 is points. That's for reflexive. This is torsion-free. This guy is locally free, and it differs from this subsheaf. So this is exactly where this guy is not locally free, right? Right? Okay. Maybe I'll just give one example, because this is actually not so abstract, this theorem. So for example, maybe I can just put it over here. On P2, take Z, a collection of points, some finite collection of points, and look at this guy, where I take the ideal sheaf of Z. So it turns out that there exist extensions of this ideal sheaf by O where this guy is locally free. Okay, if you take enough points and they're general enough, you can actually arrange for this guy to be locally free. So you get a rank 2 vector bundle on P2, and the claim here is that when you run the Yang-Mills flow, this converges to just the trivial bundle smoothly away from Z. So without knowing anything else, you know exactly what happens to the Yang-Mills flow in this particular case. So, yeah. Okay. So I can erase this now. And indeed, so in higher dimensions, there are analogous theorems. So let me just say that. So it's a theorem. So this is due to Ben Sidley, my student, and also independently by I'm having a senior moment, sorry. Adam Jacob. So in higher dimensions, so for X arbitrary, dimension, the Yang-Mills flow converges in the sense of Uhlenbeck. Oh, okay, so, sorry. I have to say something. Let me finish this statement to the Bandos-Su connection on Gur E double dual. So what is the Bandos-Su connection? So in higher dimensions, the problem now is that this is not even locally free. Right? So if the dimension of X is bigger than 3, then Gur E double dual might not be locally free. So it doesn't quite a priori make sense to talk about a Hermitian Yang-Mills connection on this guy. And so therefore we're saved by Bandos and Su, and in fact that's the origin of all of this. This convergence statement is really their conjecture. But so Bandos and Su introduced the following definition. So if, let me call it something else. So if F is torsion free, actually you can just assume torsion free here. A metric, a Hermitian metric on the smooth locus, the smooth part of F, so where it's locally free, where it's a vector bundle, it makes sense to talk about Hermitian metrics. A smooth metric on the smooth part, a Hermitian metric on the smooth part of F is admissible if the curvature of the Chern connection is in L2 and the Hermitian-Einstein tensor is uniformly bounded. So there again, we see the Hermitian-Einstein tensor and its boundedness appearing. This is kind of a theme in this whole subject, that that's the real operating thing to assume. Okay? So first of all, it's not at all obvious that admissible metrics exist. It's completely not obvious, but they prove that admissible metrics exist, and they prove the theorem that if E is stable, a stable reflexive or torsion-free, again, it doesn't really matter, but a stable torsion-free sheaf, say, let's say reflexive to be on the safe side. So stability makes sense for reflexive sheaves. The definition that I gave, of course, stability makes perfect sense for or torsion-free sheaves, actually. So if E is a stable reflexive sheaf, there exists a unique up to constant Hermitian-Einstein admissible metric. Okay, and so its Chern connection is the Bandos-Su connection that I'm talking about in this theorem. Okay, so these guys prove the higher dimensional case, and as I say, this is actually in a line of Bandos-Su's paper. They actually conjecture this. So in some sense, this is what's called the Bandos-Su conjecture. Okay, now finally, since I'm almost out of time, what about the singular set? What about the multiplicities and things? Well, over here, let me just leave this on the board temporarily. I can define the algebraic singularity, the algebraic multiplicities, pretty much the same way. So here, let Zj be the codimension 2 components, irreducible components of Z algebraic. So I'm in the same setting here. I'm going to look at this singular set. It could be very crazy, but it lives in codimension 2 just by this statement about reflexive sheaves. So I'll look at the pure codimension 2 piece, and I'll look at the irreducible components of that, the Zj's. And I'll define a multiplicity to be the rank of the bundle or the sheaf, the torsion-free sheaf, on Zj, defined by the definition here. Okay, so living on this codimension 2 piece, I've got a torsion-free sheaf, and so that has a well-defined rank, and that'll be the multiplicity. So that's the generalization of what I said before in the case of skyscraper sheaves. Okay, and now how about the generalization of this equation here? So that was done by Tian and Hong and Tian. So there's, maybe I can say there's a theorem of basically Tian and Hong and Tian. Let me just save time and just keep referring to this statement about Uhlenbeck compactness that I had on the board over here. So the theorem, I'll just paraphrase a little bit, is that the analytic singular set is a holomorphic subvariety it's completely non-obvious from the way that I've defined it. And so if Zj analytic are the pure codimension 2 irreducible components, then there's a multiplicity, Mj analytic, that's defined, that comes out of the proof of this statement, actually. And let me just tell you how it's characterized. It's such that if omega is any form, a smooth, I guess, so if x, does x have a dimension? So if the dimension of x is n, say, so if I take a smooth 2n minus 4 form, then the limit of 1 over 8 pi squared of the integral over x of the trace of Faj, wedge Faj, wedge omega, is equal to 1 over 8 pi squared. The trace of F infinity, wedge omega, and then plus a sum of these analytic multiplicities over the irreducible components of the integral of omega. So in some sense, it's saying that the second Chern form converges as a current. It's not quite saying that, I think, but it's basically saying that the second Chern form converges as a current to the limiting current plus the current defined by these analytic subdiagonals. Yeah, so it's a current, so I have to tell you what it does to an arbitrary omega. That's basically what this is saying. Okay, it's flashing red over here, so I have to state the last theorem, and that's Sibley and me, that Z algebraic is actually equal to Z analytic and the multiplicities agree. Okay, so I'll stop there. Thanks. Oh, yes, thank you. So this part, at least, has been generalized by Jiayu Li and Xizhang to the Higgs case. For this one, so to my knowledge, they haven't, what is the question exactly? So now you have a filtration by Higgs subsheaves, and so everything is the same. The only thing that I don't think anybody's really done, but I think it must be the same as well, is the singular set question. But I think that that's basically the same. Again, in some sense, one would expect this because the Higgs field is uniformly bounded, as we pointed out. So, yeah. It's not going to cause any more analytic difficulties. Oh, yeah, right. Yeah, very good question. So, yeah, so in the original four-dimension problem, this is what's called bubbling. It's bubbling phenomenon, and so this is an instanton that is bubbling off a charge m instanton, where m is that multiplicity. So in some sense, one should imagine that if you rescale a little ball around this point and look at what's happening to the sequence of connections, then I rescale, and so I bubble it off, so I'm thinking of something taking place on S4, then what I'm getting there in the limit is a charge m instanton on S4. So that's the intuition. Yeah, yeah, that's also a very good question. We basically use that to prove this part of the theorem, but I'm very unhappy with the way we do it. Somehow, one should know more. One should really have a more precise understanding of what's happening there. And so we just do as much as we need to get this statement. But exactly. That's right, but the scales are different. And so there ought to be some better understanding. And so Hsu thought that one should have some multiplier ideal sheet that kind of describes the whole picture, but I don't think that's ever really been worked out carefully. But definitely there's a better there should be a better understanding of what's happening.